Welcome back. This is Module 2, Session 2.1, Learning Paradigms, Supervised versus Unsupervised Learning. And the subtitle on this title card says it exactly right: How Machines Make Sense of the World. In the enterprise world, you will hear the terms supervised and unsupervised learning thrown around constantly. But for us, understanding the distinction isn't just an academic exercise. It's the difference between building a model that predicts your quarterly churn rate and one that discovers a customer segment you didn't even know existed. Let's get into it.
This slide is titled The Black Box Limitations, and it's one of the most important slides in this entire course because it forces us to confront exactly why standard language models fail in real production environments. Look at the diagram. On the left, you have a user query. What happened in the 2024 Olympics? That query enters the model's internal training data represented by this large brick-colored block. The model processes it, tries to find the answer, and crashes into the wall on the right. That wall is labeled October 2023 Training Cutoff. 3 failure modes emerge. First, knowledge cutoff. The model cannot give you information about events after its training ended. It will literally say, "I don't have information about 2024 events." That's not a bug. That's a fundamental architectural constraint. Second, no domain knowledge. The model has never seen your internal HR files, your product catalog, your contracts, or your proprietary processes. It will say, "I don't know your company's refund policy." It simply doesn't have access. And third, and this one is the most dangerous, hallucinations. When the model reaches the edge of its knowledge and there is no good answer available, it doesn't say, "I don't know." It invents an answer, confidently, plausibly, completely wrong. It might give a customer a fabricated address for your Boston office, and the customer will trust it because the model said it with full confidence. This is the problem RAG was designed to solve.
This slide gives us the solution, and the title says it perfectly: Breaking the Box, Retrieval-Augmented Generation. The subtitle is what I want you to focus on. Give the locked scholar a live, secure search terminal. That is RAG in one sentence. We aren't unlocking the model. We aren't changing what it knows. We are giving it a terminal, a way to search your external enterprise data in real time before it generates any answer. Look at the flow diagram. It starts on the left with a user query. What's our refund policy? That question does not go straight to the model. Instead, it first hits what's labeled as a large external enterprise data store at the bottom. 3 steps unfold. Step 1, retrieve. The system searches your proprietary knowledge base for the relevant context. In this case, it finds the company policy document. Step 2, augment. That retrieved context is injected directly into the user's prompt. The model now sees both the question and the specific text that answers it. Step 3, generate. The LLM reads the context and produces an accurate answer with a citation. You can see the output on the right. A refund policy allows returns within 30 days, and there's a footnote, number 1 in brackets, linking back to the source document. This is the core RAG loop. Retrieve, augment, generate. 3 steps completely transforms what an LLM can do in an enterprise context. And notice, the model's weights never changed. We simply gave it better information at inference time.
Now I want to address the question that every architect and CTO asks: when do I use RAG and when do I use fine-tuning? This slide gives you a definitive answer. The title is The Diagnostic Matrix: RAG versus Fine-Tuning. And the matrix compares these two approaches across 6 critical dimensions. Let me walk you through each one. Primary use case. RAG wins for knowledge-heavy tasks and Q&A, Anything that requires accessing specific facts, documents, or frequently changing information. Fine-tuning wins for you need to change the model's behavior, its style, its tone, the way it structures responses. Cost to implement. RAG is low cost. We're talking hundreds of dollars to set up. Fine-tuning can run into the thousands or even tens of thousands of dollars, plus ongoing compute. Speed of deployment. With RAG, you can be operational in hours to days. Fine-tuning requires days to weeks of training time just to get started. Knowledge updates. This is where RAG absolutely dominates. With RAG, when your policy changes, you update the document in your database. That's it. The model is immediately current. With fine-tuning, you have to retrain the entire model. Slow, expensive, disruptive. Hallucination risk. RAG produces lower hallucination risk because the model is explicitly grounded in external documents you provide. Fine-tuning relies on memorized patterns, which can drift. Data requirements. RAG works with raw, unstructured documents, PDFs, Word files, anything you have. Fine-tuning requires highly curated, labeled input-output pairs, far more preparation overhead. The bottom line? Use RAG for knowledge, use fine-tuning for behavior. Often you'll use both together.
This slide introduces what I call the blueprint, the engineering reality of RAG. The title is The RAG Pipeline, a two-phase architecture. And these two phases are everything. Look at the diagram. It's divided by a vertical line on the center. On the left is phase 1, indexing, labeled as offline preparation. On the right is phase 2, querying, labeled as real-time execution. These two phases happen at completely different times, and understanding that distinction is critical. Phase 1 is the setup work. You do it once or whenever your documents change. Phase 2 happens every time a user asks a question. These are fundamentally different operations. In Phase 1, the indexing pipeline, you start with raw documents at the top. Those documents flow into a document loader, which reads and parses your files regardless of format. Then they move through a text splitter, which breaks them into manageable pieces. Those pieces go through an embedding model, which converts text into mathematical vectors. Finally, those vectors land in a vector database, your searchable library. In Phase 2, when a user submits a query, that query flows in from the top right. It immediately hits a vector search operation, which finds the most relevant chunks stored in that vector database we built in Phase 1. The results flow into prompt augmentation, where the context is assembled and injected. That augmented prompt goes to the LLM, and the LLM produces the final answer at the bottom. This architecture is elegant precisely because the expensive work, the indexing, happens offline. Real-time responses stay fast.
Now let's zoom in to Phase 1 in detail. The title is Phase 1, the Indexing Machine, transforming unstructured files into mathematically searchable vector space. The slide shows 4 stages in sequence, each with a distinct visual. Stage 1, unstructured documents. Look at the pile of files on the left. PDFs, Markdown files, CSV spreadsheets, code files. This is your raw enterprise knowledge base. It's messy, unorganized, and in many different formats. That's fine. RAG works with whatever you have. Stage 2, document chunking. Those raw files are broken into smaller pieces, chunks. The visual shows the large document block being sliced into smaller pieces. Why? Because language models have a context window, a limit to how much text they can process at once. You can't feed a 500-page manual into a prompt. You need to extract only the most relevant pieces. Stage 3, embedding model. Each chunk goes through an embedding model, something like OpenAI's
text embedding 3 small. Look at the geometric shape in the center of the slide, that diamond wireframe with numbers emerging from it. The model converts text into a list of floating point numbers. Those numbers represent meaning in mathematical space. Concepts that are semantically similar end up close together in this space. Stage 4, vector database. All those mathematical vectors are stored in a vector database, shown on the right as a three-dimensional grid structure. This is your searchable index. Pinecone, Weaviate, and Chroma are popular choices. This database is what makes instant semantic search possible when a user asks a question. 4 steps, 1 purpose: making your documents machine searchable at the speed of math.
This slide addresses one of the most critical decisions in any RAG implementation: chunk size. The title is the Goldilocks scale of document chunking. And the Goldilocks analogy is exactly right. Chunks that are too small cause one set of problems. Chunks that are too large cause different problems. You need to find the sweet spot. Look at the scale across the top. On the far left, 128 to 256 tokens, too small. On the far right, 2048 or more tokens, too large. In the middle, 512 to 1024 tokens, just right. Here's why chunk size matters. When a user asks a question, the system retrieves the top K most relevant chunks. If your chunks are too small, you get very precise matches, but the model receives tiny fragments with no surrounding context. The answer might be technically correct, but lacks depth. If your chunks are too large, you're feeding enormous walls of text into every prompt. The retrieval becomes imprecise because a large chunk covers too many topics. The model has to wade through a lot of irrelevant content to find the answer. 512 to 1024 tokens, the just right zone, gives you a meaningful unit of thought, enough context to answer a question fully, small enough to retrieve precisely. Now look at the bottom right of the slide. There's a critical detail: the 10 to 20% overlap. When you split documents, you don't make clean cuts. You let chunk 1 and chunk 2 share a strip of overlapping text. Why? Because a key sentence might straddle a boundary. Without overlap, you'd lose it. With overlap, you catch it from both sides. The practical rule of thumb: start at 512 tokens with a 50-token overlap. Tune from there based on your evaluation results.
We've indexed our documents. Now let's talk about what happens when a user actually asks a question. This is phase 2, and this slide calls it the query funnel, connecting the user's intent to the stored vector knowledge. Follow the flow on the left side of this diagram. A user types, "What's the refund policy?" That question enters the system at the top left. It immediately passes through the embedding model, the same type of model we use during indexing. The query gets converted into its own vector, a sequence of numbers like 0.019, negative 0.142, 0.876, and so on. That query vector is then used to search the 3D vector database shown in the center. The database performs a mathematical comparison. It finds the chunks whose vectors are closest in meaning to the query vector. The closest match gets highlighted in green. That's your retrieved context. Now follow the right side of the diagram. The retrieved text, "Our refund policy allows returns within 30 days, flows up into an augmented prompt template. This template combines the retrieved context with the original user question into a single structured prompt. That augmented prompt goes to the LLM, shown here with a key detail: temperature set to 0.0. This is important. In a production RAG system, you set the model temperature to 0 to ensure deterministic, factual answers. You don't want the model to be creative. You want it to be precise. The output? Our refund policy allows returns within 30 days. Correct. Grounded. Citable. This entire operation, from user query to final answer, happens in under 2 seconds in a well-tuned system.
This slide unlocks the mathematics behind why semantic search actually works. The title is The Math of Meaning, Semantic Search. Embeddings map concepts in high-dimensional space using cosine similarity. I want you to look at the plot on this slide carefully. It's a two-dimensional graph, but understand that in reality, embedding models operate in hundreds or thousands of dimensions simultaneously. We're simplifying to 2 dimensions to make it visible. There are 3 points on this graph. The dark blue dot in the upper right is labeled Query Refund Policy. The olive green dot right next to it is labeled Chunk 1, Returns within 30 days. Notice how close these 2 points are to each other. The similarity score is 0.95, nearly identical in semantic space. The gray dot in the lower left is labeled Chunk 2, Shipping Costs $5. It's far away from the query point, similarity score of only 0.15. Here's what this means in practice. The user typed refund policy. The document chunk says returns within 30 days. These phrases use different words, but they share nearly identical meaning. The embedding model understands that refund and returns are conceptually equivalent. That's the power of semantic search. The text at the bottom of the slide makes this explicit. Semantic search relies on mathematical distance, meaning it understands the concept of a refund even if the exact keywords do not match. This is a fundamental breakthrough over keyword search. Traditional search would miss returns within 30 days if you searched for refund policy. Semantic search finds it because it understands meaning, not just words.
Let's make this concrete with a real-world scenario. This slide presents the enterprise ROI diagnostic, fine-tuning a Llama 2 70 billion parameter model for enterprise customer service. Same model, same task, same data. 2 different approaches. On the left, full fine-tuning. Hardware need? An 8 GPU cluster of NVIDIA H100s, the most powerful data center GPUs available at roughly $10,000 each. Training time? 7 days of continuous computation. Cloud compute cost? Over $50,000. And that's just for one training run. If your results aren't satisfactory and you need to adjust hyperparameters and retrain, that's another $50,000 and another week. On the right, QLoRa. Hardware need. A single RTX 6000 GPU, a high-end professional workstation GPU. Training time, 1 day. Cloud compute cost, approximately $500. Read that comparison again. Same 70 billion parameter model, same goal. $50,000 and 7 days versus $500 and 1 day. The bottom banner states the business transformation precisely. Parameter-efficient fine-tuning shifts custom AI from a capital expenditure to an operational experiment. This is not a marginal improvement in efficiency. This is a complete restructuring of the economics of custom AI. With QLoRa, your team can run 10 experiments, testing different datasets, different hyperparameters, different training strategies for the cost of a single full fine-tuning run. The speed of iteration alone is a competitive advantage. Any executive evaluating a custom AI initiative today should have this slide in front of them.
You've done hybrid search, you've retrieved your top results, but there's still one more optimization layer before those results reach the language model. This slide covers cross-encoder re-ranking, and the subtitle says it precisely. Vector search retrieves broadly, re-ranking orders precisely. Look at the diagram. On the left, you have initial retrieval, the messy stack. It's literally drawn as a tall, disordered pile of document slabs. Your hybrid search returned 20, 30, maybe 50 results. They're roughly relevant, but they are not sorted by quality. The most relevant chunk might be buried at position 15.
If you feed this messy stack directly to the LLM, you have a real problem. Research has shown that language models perform significantly worse when the most relevant context isn't at the top of the prompt. This is called the lost in the middle problem. Context buried in the middle of a long prompt often gets ignored. The solution is the cross-encoder re-ranking model, shown as the filter element in the center of the diagram. The cross-encoder takes each retrieved chunk and compares it to the original query in a deep, pairwise fashion. This is more expensive than vector search, but you're only running it on your top results, not the entire database. The output, shown at the bottom as the perfect stack, is a tightly ordered, high-quality selection of the most relevant chunks. The rest get discarded, shown on the right. The callout box on the bottom right says it clearly. Ensures the LLM gets the most relevant context at the very top of its prompt. In production systems, this single optimization step routinely improves answer quality by 20 to 30%. It is absolutely worth the added compute.
You've built the pipeline. Now the question is, how do you know it's working? How do you measure quality? How do you find the bottleneck when answers start degrading? This slide answers all of that. The title is Evaluating RAG in Production. Systematic evaluation using frameworks like RAGIS to identify pipeline bottlenecks. Look at the triangle in the center of this slide. 3 nodes connected by arrows, rotating in what the diagram calls an iterative improvement process. Those 3 nodes represent the 3 dimensions you must measure. Top node, faithfulness and answer relevance. The question here is, does the generated answer contradict the retrieved context? And does it actually address what the user asked? This evaluates your LLM and your prompt engineering. A low faithfulness score means the model is hallucinating, making up content that isn't in the retrieved documents. Right node, context relevance. The question is, does the retrieved context actually contain the answer? This evaluates your chunking strategy and your embedding model. Low context relevance means your search is returning chunks that sound similar but don't actually have the information needed. Left node, retrieval quality, measured as recall and precision at K. Of the top 5 results you retrieved, how many are actually relevant? This evaluates your vector database and your search configuration. The cycle works like this. You establish a baseline, you hypothesize where the problem is, you tweak one parameter, and you measure again. That's the iterative improvement loop shown by the arrows connecting all 3 nodes. The RAGIS, Retrieval-Augmented Generation Assessment System, framework automates the calculation of all 3 metrics. It is the standard tool for RAG evaluation in production. Measure everything, fix the weakest link first. We have arrived at the final slide of Module 2, and this one is worth stepping back to appreciate. The title is The Enterprise AI Stack, and the subtitle says, Fine-Tuning for Behavior, RAG for Knowledge. This is the complete modern enterprise AI paradigm, visualized as a 3-layer architecture. Look at the exploded diagram, 3 stacked layers, each with a distinct role. At the bottom, the engine, the pre-trained foundation model, something like Llama 3 or GPT-4 or Gemini. This is the raw intelligence, billions of parameters trained on the entire internet. It understands language, reasoning, and logic at a deep level, but it knows nothing about your company. In the middle, the personality, the fine-tuned PEFT or LoRa adapter. This is the layer that gives your model its specialized behavior, your brand voice, your formatting standards, your domain-specific communication style. As we covered in session 2.2, this adapter is lightweight. It sits on top of the foundation model without replacing it. At the top, the brain, the RAG pipeline. Real-time facts, proprietary knowledge, and citations. This is the live connection to your enterprise data. Every time a user asks a question, the RAG pipeline retrieves the most current, most relevant information and feeds it into the model's context. The example on the right of the slide brings it together. A fine-tuned customer service model, natively speaking your brand voice, seamlessly running RAG over your proprietary company documents. That is the target architecture. This is how the world's most sophisticated AI systems work today. 3 layers, each serving a distinct purpose. Together, they create something that is intelligent, aligned to your brand, and grounded in your facts. You are now equipped with the full architectural knowledge of Module 2. Module 3 takes us into prompt engineering, the art and science of communicating with these systems precisely and powerfully. I'll see you there.